Hi everyone, today we will discuss exponential function, logarithmic function, their properties, operations on these functions. So let us see how the behavior of the exponential function as well as the logarithmic function happens. So here if you consider f of x is equal to a to the power x. So if we consider this function f of x equal to a to the power x, then this kind of function or these kinds of function, they are termed as exponential function, provided certain conditions are met, like a should be positive, a is greater than 0, x belongs to real number, such that a to the power 1 it is equal to a, and if a to the power x into a to the power y, if this operation is performed and if it is equal to a to the power x plus y, then this will be treated as exponential function. So here we have to just consider that if f of x is equal to a to the power x, a to the power 1 is equal to a, and a to the power x into a to the power y is equal to a to the power x plus y. If these conditions are satisfied, then f of x equal to a to the power x is your exponential function. Here we can see f of x, if you write suppose x square, x cube, so these are simple algebraic functions. Because here x is the variable, f of x or y if you say, that is also a variable, but here the power it is 2, here it is 3, similarly we can take x to the power 4 and so on. So those are constant terms. So here it is variable to the power constant, but here it is constant to the power variable. X is variable, a is constant. So when a is constant and x is variable, so such type of function that is defined as the exponential function. So that's the basic difference as far as this exponential function is concerned or simple algebraic functions are concerned. So now, so here we can see, if we take this example, suppose y is equal to 81 to the power x. If we take this as, because here the argument x, here this argument x, for it is always real, as we have already discussed, x is always real. This x here it is termed as argument. So that argument x is always real, as well as only positive numbers. The function values only positive numbers. It means this f of x or this y, it should always be positive. So if you consider suppose y is equal to 81 to the power x, in that case we can get x is equal to 1 by 4 for different values of y. If we take y is equal to 3, y is equal to minus 3, y is equal to 3i, and y is equal to minus 3i, where I is your imaginary quantity. I is an imaginary quantity. So if we take x is equal to 1 by 4 here, then we will get 4 values of y is equal to 3, y is equal to minus 3, y is equal to 3i, y is equal to minus 3i, and so on. So out of these 4 values, we will accept only y is equal to 3, because the condition is it should be a positive quantity, f of x or that y. So these are defined only for the positive quantity, that y it should be positive. So considering this x equal to 1 by 4, we are getting 4 values, but out of those 4 values, under the definition of this exponential function, we will take y is equal to 3. So these are the properties as far as the exponential function is concerned. The standard form of this exponential function is y is equal to a to the power x is your variable here, and a is constant. I hope this is clear. So let us see. Now here if you see the graph of this function y is equal to a to the power x, for a is equal to 2 or a is equal to 1 by 2. Okay. So if we observe the graph or the behavior of this function y is equal to a to the power x, considering a particular example for a is equal to 2 or a is equal to 1 by 2. So here you can see this is the graph of the function y is equal to a to the power x when a is positive greater than 1. If a is greater than 1, because if you consider suppose y is equal to a to the power x. So if we consider x is equal to 0, just consider x equal to 0. So in that case y is equal to how much? A. So y is equal to a. If we consider if we take any particular value of a, let us say 2, then it will be 2 to the power x. In that case, if you consider this origin, that is 0 0, or taking x equal to 0, so this 2 to the power 0, that becomes how much? 2 to the power 0, it will be equal to 1. So here you have this 1. So y is equal to 1, whatever be the value of this a, but if x is equal to 0, it will be equal to 1. So in that case, you can see this x is equal to 0, y is equal to 1 we are getting. So here this graph or this graph, this is when a is equal to 1 by 2. It means in this interval a lying between 0 to 1. So in this interval a lying between 0 to 1, we have this graph. When a is greater than 1, we have this these dotted curves you can see. So this graph at 0 1 and x equal to 0, in that case y will be equal to how much? 1. So this becomes the point of intersection of both the graphs, either this or this. When we say both the graph, either in this interval as well as in this interval. So both the graph intersect at 0 1, x is equal to 0 as well as y is equal to 1. How it happens, that you can see. Take any value of this a, but if x is equal to 0, y is always 1. So this is the point of intersection. Here it is the behavior. Here if you stretch this line, this side or this side, then this curve or this curve, it becomes parallel to x-axis. This becomes parallel to x-axis, and this side also it becomes parallel to x-axis. So these are the behavior as far as the graph of the function y is equal to a to the power x is concerned. So now you can see the property of this exponential function. So either you write y is equal to a to the power x. So this is in general as far as this parameter a is concerned. Now we can have a particular value of this a, and that is your y is equal to e to the power x. E stands for exponential function. So if you take y is equal to e to the power x as a particular function as far as this behavior or this constant a is concerned, in that case also you can observe the graph of this function y is equal to e to the power x, or y is equal to e to the power minus x, or e to the power 1 upon x. So this is the graph for e to the power minus x, and this is the graph for e to the power plus x. Here you can again check that point 0 1. This is 0 1. Coordinate here again it is 0 1. So behavior it remains same. Only thing is there we have a constant a. It can be a, it can be b, it can be c, anything. Here we have that as an e. E stands for your exponential function, but the nature of the graph that will remain same. Only thing is depending on the value of a or depending on the value of e, slightly the behavior of this curve or this curve, it will be changing, because the value it can change. So depending on that the behavior will change, but overall the nature of the curve that will remain same. Here also it is such that it becomes parallel to x-axis. This side also it becomes parallel to x-axis. This side it goes up to infinity, and this side also it goes up to infinity. So these are the behavior. Here this side also it goes up to infinity, and this side also it goes up to minus infinity. So it is unbound. It is not a bounded curve. You can see this. It is not intersecting at x-axis, neither towards the negative x, nor the positive y, and nor the negative. It is intersecting the positive y only at this point when the coordinates are 0 1. It means x equal to 0, corresponding to that we have y is equal to 1. So you can see the property of this function. The function domain is minus infinity to plus infinity. It means this x can vary from minus infinity to plus infinity. So that is the domain of the function for y is equal to a to the power x in general, and y is equal to e to the power x in particular. Similarly, the codomain, and as far as the y is concerned, it is always positive. y is always positive. This side y is positive, this side also it is positive. The graph here, if you see the previous one as well as this, it is not going towards the negative of y axis. So it is either in the first quadrant or it is in the second quadrant. It means the y is always positive. Similarly, if you consider, this is monotonic function. When we say monotonic function, it means either it is an increasing function or it is a decreasing function. So it means it increases when a is greater than 1 and it decreases when a lies between 0 to 1. So monotonicity of a function means either the function is an increasing function or function is a decreasing function, and we have to separate the interval if it is both. If it is only increasing, we will say it is strictly increasing. If it is only decreasing, we will say it is strictly decreasing. But if a function is increasing as well as decreasing, it means then in that case we have to separate the interval in which interval it is increasing and in which interval it is decreasing. So here if you observe, when a is greater than 1, it increases. When a lies between 0 to 1, it decreases. So that's why we say that it is monotonic function. The function is unbounded. That's what we have seen. This side it is not intersecting x-axis anywhere. This side also not intersecting y-axis anywhere. Neither from this side nor from this side, and similar is the case. It means it is not bounded by x-axis or y-axis, except it is intersecting at the point at y-axis at the point 0, 1. So that's why we call such type of curve, they are called unbounded curve. It is continuous in nature. The function f of x equal to a to the power x or a to the power x, it is continuous in nature and it is non-periodic. When we say non-periodic, it does not repeat itself at a regular interval of time. It is not repeating at a regular interval of time, and that's why we say it is non-periodic function. So it is non-periodic, it is continuous, it is unbounded, and the function has no zeros. So it is not zero at any point. Yani y is never zero for any value of x, because here also you see at x is equal to 0, y is 1, it is not 0. So it is a non-zero function, we can say, because y is not 0 for any value of x. That's why we call it as a non-zero function. So these are the basic properties of the function, you can say. The domain is from minus infinity to plus infinity. Y is always positive, means the codomain is always positive. It is a monotonic function, increases in the interval a greater than 1, decreases in the interval when a lies between 0 to 1. It is unbounded, continuous function and non-periodic function, and it has no zeros. So these are the properties of the exponential function. So similarly you can see here, it is e to the power mod of x. This is e to the power mod of x, means x is always positive. X is, whether you take this in the positive side or in the negative side, we are considering the mod of x. It means only the positive part of this. So obviously you will get this curve and you will get this curve. Because mod of x, whether x is negative or x is positive, that mod of x, it is always considered as a positive quantity. So here we will consider this graph will also be only in the positive side, and this part will always be in the positive side as far as this y is equal to e to the power mod of x is concerned. Because I hope you know this function as far as the modulus function, magnitude of the function or mod of the function is concerned, they are always positive. Mod of x, it is equal to 0 if x is greater than equal to 0. Mod of x is positive. Mod of x, it is equal to x. This is equal to x. if x is greater than equal to 0, and this is equal to minus of x when x is less than 0. So here when I say x greater than equal to 0, it means this x is already positive. When I say x less than 0, so this x is negative. To make it positive, we are multiplying with the minus sign. So minus minus, it becomes plus. So finally here also it is a positive quantity, and this is also a positive quantity because this x is negative. So mod of x is positive. So corresponding to that, if you observe the graph of y is equal to e to the power mod of x, so this curve will be in the first quadrant and this curve also in the first quadrant, and x will be this mod of x that will be considered positive whether you take x value this side or x value this side. Now let us come to the logarithmic function. See, the logarithmic function, it is nothing but is the inverse of the exponential function. The inverse of exponential function, it is termed as the logarithmic function, because directly we can't operate. If you take, suppose y is equal to a to the power x in general, then we can't have normal algebraic operation over this, because we have only addition, subtraction, multiplication or division. So those rules are not working here as far as y is equal to a to the power x is concerned. To simplify such type of function, another function has been introduced, and that is termed as the logarithmic function. So if you consider the logarithmic function, so take log of both the side, that is left side and right side. We will just introduce a new function called log, L-O-G. Now taking log both the function, both the side, we will write log of this y, it is equal to log of a to the power x. Now we have certain properties of this logarithmic, certain properties have been defined for the logarithmic property, and using those property we will simplify this. So one of the property is such that we can write log of this y, it is equal to x log of this a. X log of a. So from here you can write this x is equal to log of base a y. How these things are written, we will just discuss it. So just one of the property we have used. So taking log both the side, we have log of y is equal to log of a to the power x. Now there are certain properties of the logarithmic function, and using that we can elaborate it such that log of y is equal to log a to the power x, that becomes x log a, and from there we get x is equal to log of base ay. Now how these two statements have been considered. So before analyzing this, let us see the properties or operation as far as the logarithmic functions are concerned. Here certain conditions, as we have already discussed, that if you take y is equal to a to the power x, then a should be positive, a should not be equal to 1, as you have seen the conditions that a should be either greater than 1, a should lie between 0 to 1, it is not equal to 0, it is not equal to 1. X belongs to real and y is always positive. So these are the certain conditions when we have defined the exponential. From this we get this logarithmic function. This clear? Now let us see some of the properties, and then we can easily elaborate all these operations as far as y is equal to a to the power x and its logarithmic behavior is concerned. So here log of base ax is less than 0 if x lies between 0 to 1. Log base ax, this is read as a, this a here, it is the base of the logarithm. So log of base ax, it is less than 0 if x lies between 0 to 1. So under that condition, this will be, value of this log of base ax will be less than 0. Similarly, log of base ax is equal to 0 if x equal to 1, means log of 1 it is equal to 0. Log of 1 it is equal to 0. This clear? Similarly, log of base ax is greater than 1 if x is greater than 1. If this x is greater than 1, then this entire quantity it is positive. It means simply you can consider these things. If x is greater than 1, this entire quantity log of 1 it will be positive. If x equal to 1, log of 1 it is equal to 0. Log of x it will be negative, means less than 0 if x lies between 0 to 1. So these are certain conditions and you should keep these things in mind for your any question where some inequality is required. Now if you consider log of base ax positive, if x lies between 0 to 1, see here, the inequality has changed. Here x lies between 0 to 1. Here also x lies between 0 to 1. But log of base ax is positive because we have changed the interval for this a here. Here a is greater than 1. For these three conditions, for this inequality, if a is positive, if a is positive as well as it is greater than 1. So if a is greater than 1, log of base ax is less than 0 provided x lies between 0 to 1. Log of base ax is equal to 0 provided x equal to 1. Log of base ax is positive greater than 0 if x is greater than 1 under this condition. Now if the base of the logarithm lies between 0 to 1, then what happens? So if it lies between 0 to 1, then log of base ax is greater than 0 if x lies between 0 to 1. Here it was less than, here it is greater than under this inequality. Similarly, log of base ax is less than 0 if x is greater than 1. So here you have this greater than sign, here it becomes less than sign. Here x lies between 0 to 1, so here it is greater than, provided this condition for a is there. So if a lies between 0 to 1, you have this inequality. If a is greater than 1, we have this inequality. Now see the properties as far as the logarithmic function is concerned. Log of, or you can say the operation, as we were discussing, y is equal to a to the power x, or particularly y is equal to e to the power. This e stands for exponential function. Value of this e here you can see this is 2.71828 and so on. 2.71828 1828 and so on. This becomes recurring here. So this is the value of this e, and that is the standard value because that e stands for exponentially particular function y is equal to e to the power x. Now as we have discussed, we have this y is equal to log of base ex. If you consider y is equal to e to the power x, taking log both the side, we can write log of y is equal to x log e. X log e. Now how these things are coming, so let us first consider that and then we will elaborate it further. So we have certain operations here as far as the logarithmic functions are concerned. If you have log of product of two functions, log of u into v, then that becomes log of u plus log of v. Log of u into v, it becomes log of u plus log of v. Similarly, log of u by v, here it is the division of these two terms, then here it becomes subtraction. So log of u minus log of v. Log of u to the power n, log of u to the power n, here it is in power, then that becomes n log u, and this is the relation that we are using here when we convert this. Log of u to the power n, that is equal to n log u. Similarly, log of base ab is equal to c. If you have log of base ab is equal to c, then that means b, this b here, it is equal to a to the power c. So b is equal to a to the power c. And similarly, if we consider log of base ab is equal to log of base db divided by log of base da, means this is termed as the change of base. If you consider a function log of base ab and you want to change this base a to any other base, let us say d, then that becomes log of base d, and here it is b, so it will be in the numerator. Here it is a in the base, so that will go in the denominator. So log of base dA. So log of base AB, it is equal to log of base DB divided by log of base DA. That way we have the change of the base. Now there are certain particular values. Log of 1 it is equal to 0. Log of base AA, yani base as well as this number, whatever it is, log of base AA, log of base BB, log of base CC, that is also equal to 1. And log of base E, it is also equal to 1. When we say L and E, when we say this L and E, it means this is equal to log of base EE, and that is also equal to 1. Ln, this is n means the natural logarithm. So in that case, the base of the logarithm, it is considered as E. So that becomes log of base EE, and that is equal to 1. So now let us see the inequality based on logarithmic function. So here if you have suppose log of base AB greater than C. Let us say log of base AB greater than C. Then this will be B greater than A to the power C, provided base of the logarithm is greater than 1. So if base of the logarithm is greater than 1, there will be no change in the inequality, and if base of the logarithm lies between 0 to 1, then the inequality changes. If it is greater than, it becomes less than. If it is less than, it becomes greater than. So here if you see log of base AB greater than C, B greater than A to the power C, provided A is greater than 1. Similarly, you can consider log of base AB greater than C. So B will be less than A to the power C if 0 less than A less than 1. Here the base of the logarithm lies between 0 to 1. So the inequality has changed. Here it is greater than, now it has become less than sign. So that's what you can see here. Base of the log base AB greater than C, B greater than A to the power C. Here it is greater than, so here also it is greater than. If A means base of the logarithm is greater than 1. Similarly, log of base AB greater than C, so B less than A to the power C, B less than, here it is greater than, here it has become less than, B less than A to the power C if A lies between 0 to 1. So if base of the logarithm is lying between 0 to 1, the inequality has changed. Similarly, log base AB less than C, B will be less than A to the power C if A greater than, means here again you can see there is no change in this inequality. Here it is less than, here also it is less than. And log base AB less than C, so again the inequality will change because base of the logarithm lies between 0 to 1. So here it is less than, here it will become greater than. So B greater than A to the power C. So just to conclude, we can say if base of the logarithm is greater than 1, there will be no change in the inequality. If base of the logarithm lies between 0 to 1, the inequality will change. If it is greater than, it becomes less than. If it is less than, it becomes greater than. So that way, whenever you have inequality related with any logarithmic function, so you just check the base of the logarithm, check the condition based on the base of the logarithm, and accordingly use the concept of this inequality. Now we can see the behavior of the logarithmic function as far as the graphical representation is concerned. Here if you see y is equal to log of base ax, here I have taken the base of the logarithm as a. Okay, so you can see this graph, y is equal to this log of base ax, or you can see same log of base ex, e that is the exponential function that you can see, or the exponential number. So this is for y is equal to log of base ex. Is clear? Now if x is equal to suppose 1, y is equal to how much? 0. X is equal to 1 because log of 1 it is equal to 0. So here you can see x is equal to 1, y is equal to 0. So this point, this is the point of intersection. This is your 0. This is 1, this coordinate is 1, 0. So it means it will intersect the x-axis only at one point, and that is 1, 0. Otherwise, neither it intersect y-axis this side, nor it intersect y-axis this side. This will go up to infinity this side, and this will also go up to minus of infinity as far as the y coordinate is concerned this side, and it will not touch the y axis. Similarly, again it will not intersect x-axis. There is only one intersection here, and that is 1 0. X is equal to 1, we have y is equal to 0. So this is the only point of intersection. Otherwise it will be growing like this and it will be moving like this. Here it becomes parallel to y axis. Here it becomes parallel to y axis, and here also this will become parallel to x axis. Here this is your x axis. So after moving up it becomes parallel to x axis as x tends to infinity. When this x tends to infinity, so this will be also, this curve this side also becomes parallel to x axis. So this is the behavior of the curve as far as the logarithmic function is concerned. Now you can see this graph. Now in this graph, here we have this log of base ax. This is this dotted curve, if you see. This is for the base of the logarithm when it is greater than 1, and this curve you can see when a lies between 0 to 1. A is the base of the logarithm. So when a lies between 0 to 1, we have this curve. Okay, and when a is greater than 1, we have this curve. The nature remains same. Only thing you can say, again when this x tends to infinity, this curve will become parallel to x axis, this will become parallel to y axis this side. Here this side again it becomes parallel to y axis, and this side again it will, once it gets extended, and it will become parallel to x axis. Again the point of intersection is only one, and that is 1 0. This is the coordinate of point of intersection when x equal to 1, y is equal to 0. So we have this coordinate as 1 0. Now if you see the property of this function, the domain of the function is what? Always x positive. We don't, logarithmic function is not defined as far as the negative numbers are concerned, so we have x positive. So domain is always x greater than 0. As far as the codomain, any value of the function f of x or y is concerned, so y lies between minus infinity to plus infinity, and that you can see in the graph. Minus infinity, it goes up to minus infinity, and this side also it goes up to plus infinity. So the domain, the codomain, it is from minus infinity to plus infinity. Now it is again a monotonic function. Monotonic function means increasing function as well as the decreasing function. So it increases when a is greater than 1, and it decreases when a lies between 0 to 1. So the function is increasing as well as it is decreasing in different interval as far as the base is concerned. For a greater than what, it increases. For a lying between 0 to 1, it decreases. The function is again unbounded. It is unbounded. Again here, this is the only point of intersection. Otherwise, either it is parallel to y-axis or it is parallel to negative of y-axis. Similarly, parallel to this x-axis. Here it is not bounded by x-axis or y-axis anywhere, except that it gets intersected at the point 1 0. So that's why we say the function is unbounded. Again, it is continuous everywhere, and it is non-periodic. Again, when we say non-periodic, it means it is not repeating itself at a regular interval of time. So it is non-periodic, it is a continuous function, it is unbounded, okay, and it is a monotonic function. It is increasing as well as decreasing depending on the condition of the base of the logarithm, that is whether a is greater than 1 or a lies between 0 to 1. The function has 1 0 at x equal to 1. That's what we have seen here. At x is equal to 1, y is equal to 0. So this is a 0 function, but the coordinate which satisfies that it is a 0 function is only 1, and that is 1 0. X equal to 1, y it is equal to 0. So this gives the entire perspective of the logarithmic function. We have discussed the operations as far as the logarithmic function are concerned, the inequality based on logarithmic function, the characteristic, that is the feature of the logarithmic function, as well as the graphical behavior of the logarithmic function. So in this lecture we have seen the complete picture of the exponential function as well as the logarithmic function. I hope this clears all your concepts, and in the next video, that is coming video, we will discuss problems based on exponential function, logarithmic function, their properties, graphical behavior and all that. Thank you.